How's it going, everyone? In this video, we're going to discuss the concept of projection of one vector onto another and how to calculate what the projection of one vector onto another is. So first, what does it mean? Let's say you have two vectors that we're going to call u and v. And we want to know the projection of vector u onto vector v. So here's what that means. Now the order here matters. We're projecting u onto v, not the other way around. So from v, if we draw a perpendicular line that will touch the end of u, if both vectors u and v are made to start at the same point. There's only one such perpendicular line, and that's what it looks like, what I drew here, the dashed blue line. Now, if we were to draw another vector from the point of origin of both of these vectors to the point along vector v where that perpendicular line touches, that line right there, that is the projection of vector u onto v. And that's often how it's written. Proj for projection, and then the vector that you're projecting is written in regular font, which is vector u, and the vector you are projecting onto is written as a subscript in between, and that is vector v. One way to think of it, a useful analogy, is imagine it was raining in a direction perpendicular to vector v. What area would stay dry? That's what the projection is. That's one analogous way to think about it. Of course, we're not getting into the actual physics of rain and wind coming into play and the source of the water and all that. So, how do we calculate this? Well, we have a triangle. Okay? If this is vector v, and this is vector u, and this is that perpendicular line, we want to know what the magnitude of that side is, and then we want to have a vector that points in the same direction as vector v, but its magnitude is this side of the triangle. Well, we can find that out using trigonometry. Let's say theta is the angle between them. So our triangle looks like this. This has side length magnitude u, and this has angle theta. And if we want the magnitude of the projection of u onto v, well, we know that the cosine of theta is equal to the adjacent side, which is the projection of u onto v, divided by the hypotenuse, which in our case is u. Now, we can rearrange this formula and write that the projection of u onto v, that is its magnitude, is equal to the magnitude of u multiplied by the cosine of theta. Now here's what I'm going to do. I'm going to take the right side of this equation, and I'm going to multiply and divide it by the same value, and that value is going to be the magnitude of vector v. And the reason I'm doing that is if you look at the top of that right side, that's actually u dot v. Right? The dot product between vector u and vector v is equal to the magnitude of u times the magnitude of v multiplied by the cosine of the angle between them. And the convenient thing about the dot product is that you can calculate it without knowing the angle between the vectors. So we can write that this equals u dot v divided by the magnitude of v. You can calculate this if all you know is the coordinates of these vectors without having to know the angle between them. Now this is the magnitude of the projection. If we want the actual projection, we now have to multiply that magnitude by the unit vector which is in the direction of v. So, what is that unit vector? Well, here's what it is. So the actual projection, not just the magnitude, it's going to be that magnitude u dot v divided by the absolute value of v multiplied by that unit vector. That unit vector is just vector v divided by its own magnitude. That's the unit vector in the direction of vector v, just vector v divided by its own magnitude. That is going to have a magnitude of 1, and it's going to be pointed in the direction of vector v. Now we can simplify this equation. We can write it as follows. U dot v divided by absolute value of v squared multiplied by vector v. And we can actually write this in an even more elegant way, because the magnitude of a vector squared is the dot product of that vector with itself. So we have u dot v divided by v dot v multiplied by vector v. And that is the formula for projection of u onto v. It's that simple. So, let's do an example. Let's say u is equal to 1, 4. We're just going to do a two-dimensional example. And let's say v is equal to 6, 1. And we want to find the projection of u onto v. Okay? So that is going to be equal to u dot v divided by v dot v multiplied by vector v. So we have 1, 4 dot 6, 1 divided by 6, 1 dot 6, 1 multiplied by vector 6, 1. So calculating that, we have 6 plus 4 divided by 6 times 6, which is 36, plus 1 times 1, which is 1. And here you can see why the dot product of a vector with itself is the magnitude squared. Because if you were to just square root this, well, that would be the magnitude. And we multiply that by 6, 1. So we have 10 over 37 multiplied by 6, 1. Now, I do want to graph this, so let's put things in decimal form. 10 over 37 is approximately 0.3. 0.27-ish, we'll call it 0.3. So 0.3 times 6, 1 And that gives us approximately 1.8 and 0.3. Now, let's graph it. So, there's our axis. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Right? 2, 4, 6. 2, 4, 6. Let's start with our original vector. U is 1, 4. So that would be right here. And V is 6, 1. So that would be right here. So the projection of U onto V, if we were to look at it graphically, it should be this vector here. Now let's see what our answer gave us. Well, our answer gave us a x-coordinate of 1.8, which is going to be just under 2. So that checks out. And a y-coordinate of 0.3, which should be just under halfway to 1, which also checks out. So there you go. We can see graphically that this formula, as expected, gives us the correct answer. And that's how you calculate the projection of one vector onto another. Now this example was two-dimensional, but it works for higher dimensions as well. So I hope that helps, and until next time.